The block D of mass m that equal 80 kg is released from the rest and falls through a distance h which is equal to 40 mm, and before it strikes the midpoint C. C is the midpoint here, that is distance from AC to BC is same as 0.5 meter. Using Young modulus equal to 73 gigapascal, determine the maximum deflection of the point C and the maximum stress that occurs in the beam. So because of the impact of the load, the beam will get deflected. So let's say here A to B represents here the initial position, and once the load will impacted, it will have a deformation equal to dl. So this deformation will be same as equal to dl. So if we compare the initial position, that is h plus dl has a potential head, and finally will come to the rest at this position. So we have work done will be same as equal to w into h plus dl. This amount of work done will be same as the equivalent static load that will act and will develop the same amount of deflection that equal to dl. And in case of simply supported beam, if the load is acting at the center, then the deflection dl will be equal to we into l cube divided by 48 times of ei. This one is a gradually applied load. So the right hand side of this equation will be equal to 1 by 2 into we, that is the equivalent static load, multiplied by dl. W we can write here as product of mass into g, that is mg into h plus v of dl equal to 1 by 2, and we we can write from this equation as 48 times of ei divided by l cube multiplied by dl, that is v of dl square. So we can expand this equation and we'll write the quadratic equation here. So this term we'll write first, that is v of 24 times of ei divided by l cube into dl square. Then we'll write this term and will become negative, is minus m into g into dl, and then we'll write a constant term equal to minus mgh will be equal to 0. Now we'll develop here the quadratic equation. So we have constant is equal to 24. Young modulus is given as 73 gigapascal. So we'll continue SI unit. In that case, we'll get the dl in meter. We have 73 into 10 to the power 9. I represent here the moment of inertia. We have size of a square section is 40 mm. So that will be equal to 0.04 to the power 4 and is divided by 12. And further divided by L cube. L cube is same as 1 meter. So we have 1 cube into dl square minus mg into dl. M is same as equal to 80. So we have 80 into 9.81 multiplied by dl. M is equal to 80. G is equal to 9.81 multiplied by dl. Again we have minus mgh. That is minus 80 into 9.81 is mg. H is equal to 40 mm is 0.04 equal to 0. Coefficient of dl square come out to be 373.08 into dl square. 80 into 9.81 is minus 784.8 times dl, and 80 into 9.81 into 0.01 is minus 31.39. You will get a 2 roots of dl here. You will select the positive root and you will get a positive root dl is equal to 0.01, that will be meter, or is same as equal to 10 mm. So this one is a maximum deflection of the point C. Maximum stress we can find out here once we can find out the static load. So we have static load we is equal to 48 times of ei multiplied by dl divided by l cube, that is we have 48 into Young modulus. Young modulus is 73 into 10 to the power 9. Moment of inertia is same as 0.04 to the power 4 divided by 12. dl will take in meter is 0.01 divided by l cube is 1 cube. Solve this, you will get the static equivalent load. So static equivalent load we come out to be 7745 that will be Newton. And now we can develop the SFD and the BMD. Reaction on the two support will be WE divided by 2. Because of symmetrical loading, the reaction is equally distributed between the two support A and B. In SFD, we will get two rectangle and the height of this rectangle is WE divided by 2. At A, we have shear force is equal to WE by 2. At C here, where we have a midspan, the shear force will change the sign, and therefore the value of bending moment at C will be equal to maximum value. And at point B, we have shear force will be equal to minus WE divided by 2. So this area here will give you the maximum value of bending moment. So maximum value of bending moment, that is MM max, will be equal to WE into L divided by 4. We have WE is equal to 7745. L is equal to 1 divided by 4. So this answer will come in Newton meter. So we have maximum bending moment at C is 1936.25. That will be Newton meter. Maximum bending stress we can calculate using the flexure formula. That will be equal to the maximum value of bending moment, that is mm max, multiplied by C. For a square section, our neutral axis will be exactly at halfway and the distance of C will be 20 mm, divided by the moment of inertia equal to I. Maximum bending moment will take in Newton mm is 1936.25. Newton meter multiplied by 10 to the power 3. C is the distance of top fiber or bottom fiber from the neutral axis, that equal to 20 mm, divided by moment of inertia for a square section is 40 to the power 4. Since we have taken here the C in mm, will take the I also in mm, is 40 to the power 4 and is divided by 12, that will shift in numerator. So we'll get here the maximum value of a bending stress is approximately equal to 175.2, that will be megapascal. So first you apply the work energy equation, that is the work done equal to 1 by 2 WE multiplied by DL. Substitute for WE in terms of DL, develop the quadratic equation, select the positive root. Once we know DL, calculate WE, and once you calculate WE, develop SFD. It will be rectangle in the case of simply supported beam. Find out a maximum bending moment at C, which one is the area of a rectangle A to C is WE multiplied by L divided by 4. Once we know the maximum bending moment, apply flexure formula. Flexure formula is maximum bending moment multiplied by C divided by I. Substitute all value and find out the maximum bending stress, which come out to be 175.2 megapascal. The cantilever beam shown in the figure has a span of 1 meter, that is we have value of L is equal to 1 meter, diameter equal to 30 mm. A weight of 20 Newton is dropped from a height of 50 mm, that will be equal to H, and we have weight is equal to 20 Newton. At the pre-end of the beam, Young modulus is given as 200 gigapascal. Find the maximum instantaneous deflection at the end. So because of the weight drop here, the beam will be get deflected. Let A is the point at the fixed end, B is the free end. So at point A there is no deflection, at point B we have the maximum deflection, and this maximum deflection will be equal to DL. Now here we have to apply one static load that equal to WE, such that this load when kept at the free end will also produce the same deflection. So in the case of cantilever, if the point load is applied at the fixed end, then we have deflection DL will be same as equal to WE, that is the equivalent static load, multiplied by L cube and is divided by 3 times of EI. So first we'll use here the work energy theorem. According to the work energy theorem, we have potential energy change that equal to W into H plus DL is same as equal to the work done due to equivalent static load, which one is the gradually applied load is 1 by 2 multiplied by WE multiplied by DL. Now here again we can replace WE and we can develop the quadratic equation here. So we have W into H plus DL equal to 1 by 2. W we can replace as 3 times of E into I divided by L cube, and we have DL square. So let's develop the quadratic equation here. We have 3 by 2 into E into I divided by L cube multiplied by DL square. This term will shift to the right, will be minus W into DL, and again we have minus W into H must equal to 0. So we have 3 by 2. Young modulus E is given as 200 gigapascal, so we have 200 into 10 to the power 9 into moment of inertia is pi divided by 64 d to the power 4, that equal to 0.03 meter, and we have power is equal to 4 divided by L cube. L cube is same as 1, so we have cube of 1 multiplied by DL square minus W. This time W is equal to 20 multiplied by DL minus W. W is equal to same as 20, and the height H through which the weight is dropped is 50 mm is 0.05, that will be equal to 0. So find the roots of this quadratic equation. Your answer will come in meter. We will get the value of DL is approximately equal to 0.0103, that will be meter, that is equal to 10.3 will be mm. You have to select here the positive answer. The video you are watching is from the app, which is the More Class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.